So chapter 10, what this is going to focus on is the theory behind how we can essentially believe the ideal gas law and believe all of the calculations that we're focused on here. So it's called the kinetic molecular theory of gases. And you sometimes see it abbreviated as KMT, KMT. So what I have in your notes is some space here. And what we're going to do is essentially draw a picture of each part of this theory. And again, what this theory is to essentially make it okay that the ideal gas law works the way it does. So we're going to make some assumptions or state some things of how these gases are going to behave. But in the next lecture, in the next video or two, I will talk about real gases and how they are different from the ideal gas law. But for right now, we're just going to kind of go over the theory. So gas is composed of extremely small particles that are very far apart and therefore occupy a small fraction of the total gas volume, negligible. Okay, so what this is trying to say is that the gas itself in a container, the particles themselves are so small that we don't account for their volume in PV equals nRT. So draw a box with a bunch of small little dots, and the dot is supposed to signify gas particles. Okay, so really what we care about is the volume of the container. So let's say this is a 5-liter container. So the volume that we use in PV equals nRT is always of the container, okay? Now we will account for this in the fact that the gas particles are very, very small, but we will account for this in something called the van der Waals equation a little bit later on. So again, anytime we use PV equals nRT, we always use the volume of the container. So second thing we could focus on is the particles move constantly and randomly throughout the gas volume. As a result of their motion, they undergo frequent collisions with one another and with the walls of the container. The collisions with the container result in the pressure being exerted by the gas. So how would you show that in a picture? Okay, so draw yourself a container with a gas in it. Okay, and what you want to show is essentially this gas particle is moving randomly. Okay. So they're not all moving in the same direction. And you want to show that they're hitting the sides of the container. You could also show that one is hitting another, okay, to show collision. All right. So we discussed this a little bit before. Pressure is a force per unit area. Well, really, when we're looking at gases in a container, what is the force that we're talking about is the collisions, okay? So it's really collisions. And we are talking about not area, but the volume of that container. Okay, so that's really pressure, what we're talking about. So again, we always assume that the gases are moving randomly and that the pressure is due to the collisions. That's really what that part is about. Number 3, particles do not attract or repel each other. So again, what you're trying to show in this picture is you don't have them all clumped together, okay? That's not how we envision gases. We are going to assume they have no intermolecular forces, and we will talk more about intermolecular forces in the next chapter. So what that means is each one of these gas particles is independent of each other. Now, if you have a diatomic, okay, like oxygen or hydrogen or any of those, we will draw 2 circles touching each other next to each other. But really what we're talking about here is they don't clump together. They are separate from each other, and that will be also accounted for in something we talk about later. And part 4 here, collisions of particles are what we call elastic. Okay, at constant temperature, the total energy of the system remains constant. And again, if you've had some physics, you probably have talked about collisions and other things associated with it. But if 2 particles are colliding, what we are saying is when they are leaving the collision, they're going to have the same kinetic energy as they had before. So again, if you have some physics background, you have friction and other things that take place, loss of heat when 2 things collide. We are assuming that everything is remaining constant. We're assuming everything is remaining constant. So force, when we're talking about this in terms of gases, is always going to be dependent on the frequency of the collision with the walls of the container, which depends upon the speed of the particles. So again, and also the volume of the container. So if you have a very large container, you're going to have much less frequency of the collisions because there's so much space for the gas to go, and gas will always fill the container. The speed of the particles can also be due to the mass of those particles and how quickly they move. And then the second part here is amount of translational kinetic energy for the particle through space. So again, we don't really worry about direction here. That's vectors, and again, if you have some physics background. So we're not really focused too much on, again, if there's not a direct collision, we're just talking about if two things collide, the kinetic energy is then transferred. Kinetic energy. So if we have this theory and we have made these assumptions about gases, we could then do what we call the derivation of the ideal gas law. Now again, I'm not going to spend too much time on this. So what I'm going to do is I'm going to pause the video and then kind of walk you through what I'm getting at here. So what I'm going to kind of walk through with this derivation is kind of how an equation can be derived about what I call the speed of the particle. Okay, so we know that kinetic energy of a substance is proportional to its temperature. So as I increase kinetic energy, the temperature will increase, vice versa. And we know that kinetic energy, an equation we have seen before, is 1/2 mv squared, and v being velocity. Okay, so I'm going to kind of derive an equation that's going to use velocity. So I can find what we call the kinetic average of a mole of a gas by using this equation. So I have to account for what we call Avogadro's number. So I could use kinetic energy, I could take 1/2 mv squared and just multiply by Avogadro's number. And that's going to be per mole of a gas. Okay, so that's all I'm doing in this equation. Okay. Then if I take PV equals nRT, okay, I could derive this next equation, but I just give it to you so you can kind of use it. I could find what we call the kinetic average another way, kinetic energy of the average of a mole of gas. So 3/2 RT can be derived from PV equals nRT. R has to be 8.314 joules per mole Kelvin for this, so that I end up with joules per mole for my energy unit for this. And again, this could be derived, just not going to spend any time doing that. I could also break it down into something called the kinetic energy of average per molecule. So I could take 3/2 kb times temperature. So kb is something called Boltzmann Constant, and if you've had some physics before me, you might have heard of Boltzmann, and we will talk about Boltzmann distribution in a little bit. But kb is going to be R divided by Avogadro's number. So it comes out to be about 1.38 times 10 to the negative 23rd joules per Kelvin molecule. And again, this is per molecule, so we usually don't go this far down. We usually stay in the moles, but we can use this in certain calculations. So we could then take our two equations per mole. So I could take the Na 1/2 mv squared, and I could take the 3/2 RT, and I could put them equal to each other. I could put them equal to each other because they both are saying the same thing. So I'm going to try to solve for V here. So I'm going to multiply both sides by 2, so you get rid of the 2. And so what you're left with is 3RT over on the left. And then I'm going to bring the Na over on the left, dividing it. And then I'm also going to bring the M over here as well. Okay. And that's going to be equal to velocity squared, So how do I get rid of the velocity squared? Well, I take the square root of both sides. So I'm left with the square root of 3RT over Na times mass. Well, what does that happen to be? Well, that happens to be the molar mass of the gas. So the velocity of a gas is going to be equal to the square root of 3 times R times T over the molar mass. Now the R has to be 8.314 joules per mole Kelvin for this equation to work, but it does work. And again, it goes back to molar mass and units that we will talk about.